Hello, I'm Scott Peterson from Intel. I'm here today to talk to you about Adaptive Distributed NVMe-oF Namespaces. This is a system we've devised to help NVMe-oF fabrics work with cloud scale and large enterprise scale storage systems. We will start out by comparing NVMe-oF fabric systems to scale-out storage and describe why you'd want to use NVMe-oF fabrics with those, what the advantages or relative advantages and disadvantages are, and what you might have to do to make them fit together. We'll then cover what ADNN does and how that improves NVMe-oF fabrics for that use case. Then next, we'll dive into the details of how ADNN works. We'll cover the familiar design patterns that are reused there and the basic building blocks that we've devised to construct those systems. We'll next go into the experimental results we got with our reference implementation of ADNN with Ceph as a backend. Ceph being, an existing sort of the poster child cloud scale block storage system. Everyone knows about it, and so it's a good target for experimentation. Then we'll talk about the availability of the ADNN reference implementation in SBDK, where you can get it and what needs to happen next with that. So here we describe NVMe fabrics and a scale-out block storage system side by side with their relative advantages and disadvantages. The good points are, of course, shown in green, and the potential shortcomings are listed in red here. So starting with NVMe fabrics, obviously it's an industry standard. NVMe and NVMe fabrics are industry standards. It's high performance, low latency. At least NVMe, every OS basically has an NVMe driver, and most of them have NVMe fabrics drivers. The footprint is low. The CPU and memory utilization for the client is low. It's basically a small amount of code. These things could easily be offloaded into SmartNICs and have been. On the other hand, NVMe fabrics connects your host to single devices. Basically, it's a point-to-point connection between a device and a host or several hosts. The NVMe fabrics backends tend to be simpler. They tend to lack sophisticated volume services like clones and snapshots, things like that. Now compare that to scale-out block storage, which of course starts with scale. It's high capacity and scalable performance. Because it's large scale, it of course has to have HA and self-healing capabilities, or it wouldn't work at all, but this becomes an advantage. These tend to have richer volume services. Ceph can do clones and snapshots, things like that. Thin provisioning. Your NVMe fabrics JBOFs might support thin provisioning or might not. The cost of the custom or the scale-up block storage tends to come in the form of a bespoke client that must be installed on your host. If you're using multiple scale-out backends, you'd need one of each. Gluster and Ceph at the same time, you'd need to somehow combine those things. These things are often not small or particularly high performing. Often just the fact that you have to integrate it with the host is enough of an obstacle. These things combine to make offloading these clients into a SmartNIC fairly challenging. So in these diagrams at the bottom, we show on the left here a bunch of hosts connected to their volumes in their color, and you can see that we've represented each volume as being in a particular place, a single storage node somewhere on the fabric. Compare that to the right, where these same hosts are using the same volumes, but in the diagram, you can see that the volumes themselves are divided up and stored in extents on different storage nodes, and that's the key distinction that ADNN addresses here. So we asked ourselves, what if we could combine NVMe fabrics with the scale of the scale-out storage backend and get the best of both worlds? So our goal here is to combine only the good things from the previous diagram. So we want an industry standard interface. We want it to be high performance and low latency. We want every OS to be able to talk to it. The footprint to be small enough that you could put it in a smart NIC or some other hardware object. But we still want to preserve the rich volume services and all of the advantages you get from your scale-out storage system. ADNN accomplishes this by adding an NVMe-oF Fabrics target to all of the storage nodes in the distributed block storage system. And we add a component called a Redirector in the hosts and all the storage nodes, which has the ability to learn the locations of the extents of the volumes that the host uses. So this diagram at the right will show an example of how this works in the form of two IOs to the same region of a logical namespace. And this logical namespace, in this example, is stored on storage node 1 on the left and on storage node 2 on the right, meaning that in this case, the first half of the logical namespace is in node 2 and the second half is in node 1. So in this example here, the host is connected to both storage nodes, but doesn't yet know where its extents are. The storage nodes do know that. They are the distributed storage system, and the logic in the distributed storage system chose those locations and does know that. So in this scenario, the host doesn't yet know that, so it sends an IO with labeled here with the blue label next to the 1 to storage node 1 to try to get to, say, LBA 0 of its namespace. Now, this was a bad choice, but it didn't know that yet. Storage node 1 does know that LBA 0 is on node 2, so it forwards that IO to node 2 via some unspecified mechanism that the distributed storage system uses. We say unspecified because there are a number of options, and we'll get into that later. Now, the redirector in node 1 that forwarded this IO takes this opportunity to inform the host that LBA 0 is actually on this other node. It should send it to node 2. Meanwhile, it's completing this IO to node 2. We don't show the completion messages coming back. That would just make this chart too busy. But from the host's point of view, it's IO completed, and it was told, don't do that again. Do it over here. So the next IO number 2, the red one, that the host sends, it now has the benefit of that hint. You see the arrows pointing to the hint table here indicate that the redirector and the host can consult these hints to make a better choice next time. So the second time it sends an IO to LBA 0, it now knows it should go to storage node 2. And so now ADNN has achieved getting the host to send the IO to the right place most of the time. In fact, we think that often the hosts will learn all these hints when they initially connect. So there may not actually be any learning in response to an IO that actually has to occur. But the guidelines here are that all the storage nodes in an ADNN system can deliver all the IO to the logical namespaces that they present to a host. Some of them do it more efficiently than others. And the host doesn't have to have perfect knowledge of where things are. It will work without it, but it works much better when they do get it. So this allows a looser coupling between the actual distributed storage system and the hosts. This is all based on log pages, basically. So we say no new standardization is necessary because it uses existing NVMe mechanisms to do this. Now, ADNN would benefit from some standardization, obviously, if you'd like these things to interoperate. But what we mean by that is that we don't radically change NVMe at all. So the components that make an ADNN system work are, of course, the redirector. This is a software or hardware building block that is reused everywhere in the system, meaning you'll have one in every host and one in every storage node. There's logically one redirector per namespace. It has state that's specific to that namespace. So there's maybe one instance of a redirector software there, but obviously there's multiple running instances of its state. The redirector selectively forwards IO to functionally equivalent targets based on the address of the IO. That's its distinction from, say, multipathing, which would either distribute all the I/O round robin or choose the best working path. A redirector learns better destinations for each I/O from its adjacent redirectors. That applies in general to an arbitrary graph of redirectors, but here we're going to restrict ourselves to systems that have host redirectors and some number of egress redirectors in the storage backend. Redirectors are also used in storage nodes. In that case, they are configured explicitly by the storage system, which of course knows where each part of the I/O really lives. And that they're basically the redirectors in the storage nodes are the last hop to the actual media. The next important component is the location hints themselves. These are the unit of placement that a redirector uses to make its I/O routing decisions. Location hints can take many forms. The simplest just define a starting LBA and a length and name one target NQN. And they say that all the I/O for this range should go there. Others may define a striping pattern across an array of targets. They may say the entire volume or this range of the volume is striped this many stripes of this strip size across this list of targets. And others may be more complex, like in the case of Ceph, where the hash function needs to be executed to determine which target an individual I/O goes to. And so the last component, which isn't really a component, more of a concept, is the distributed volume manager. This is an abstraction we defined to represent the interface that your distributed block storage system would present to ADNN hosts to make an ADNN system. The DVM concept defines roles for redirectors, as this is where the notion of a host redirector and an egress redirector comes from. The idea is that it's all the same redirector code, they're just placed in different places in the system and they're configured differently. The DVM abstraction is defined to help support stateless configuration of clients. They ideally provide a discovery service that identifies to the clients all the target subsystems in the distributed volume manager, and there's mechanisms provided so that a host redirector, well, you'll see this later, a host redirector can discover from its targets what its namespace properties are. We'll cover that later here. So the redirector itself is, like I said, the basic software or hardware building block in an ADNN system. Its essential job is to accept I/O and then choose one of its available targets as the destination for that I/O. So it, of course, has to be configured with a number of targets. If this is in the host, like I said before, that should be from a discovery service. Inside the distributed volume manager, that's probably explicitly configured. Inside the redirector is a construct called or an internal data structure called the mapper table. Now the redirector transforms all the hints it has learned from its targets, which may conflict with each other, be ambiguous, refer to targets that it's not currently connected to, etc. When those things change or targets come up and down, the redirector generates its mapper table. The mapper table maps LBAs of the namespace to specific targets. And basically, until the mapper table changes, it defines how I/O or where each I/O to each LBA would be delivered by this redirector. Some redirectors, specifically the ones in the DVM, will get their hints from some piece of control software, the entity that actually manages the placement of data and is the arbiter for which nodes are up and which nodes are down. That entity inside the distributed storage backend will provide hints to redirectors that are considered authoritative. And an authoritative hint is never overridden by one that you've learned. And it's always the hint that you'll provide to the redirectors connected to you. It's the source of truth about placement. And egress redirectors that get authoritative hints just continue to use them until they're told to do otherwise, because they don't really know any better. A redirector conceptually always forwards I/O to other redirectors. In the case of a host redirector, that's obvious. I/O comes in through some binary interface, a function call or a bus function, and it's going to send it out the fabric to one of several targets. Inside the storage nodes, a similar thing happens, and I/O comes in and it's going to forward it, you hope, to most of the time to a local device. So because the redirectors in the storage nodes must all be able to complete I/O to any LBA in that namespace, they obviously have to have a path to deliver it. So if your distributed block storage system consists of a bunch of separate hosts on the fabric, or maybe a pair of fabrics, that mechanism may be another NVMe over fabrics connection, meaning your storage nodes may have NVMe over fabrics connections to each other. The egress redirectors in those storage nodes may forward I/O that arrives at the wrong place over, say, its private fabric connection to the right place. If you've got, say, a multi-node, or say a two-node block storage system with a private PCI bus and all your SSDs are dual ported, then your forwarding might get a lot simpler. You might be able to just address that SSD directly over the inter-chassis interconnect. You could simplify that down even to a two-socket system, where some SSDs are on NUMA node 0 and some are on NUMA node 1, and if the I/O arrives on the NIC in the wrong NUMA node, you can just complete it because you can see that SSD. It just performs a little more slowly. So the basic concept of a redirector is that they learn from their forwards and they take the direct path next time. And in fact, we hope that they take the direct path the first time. And whether they can do that or not depends on whether your storage system can be described in few enough hints that they can be provided to all the hosts when they connect. So, like I said, location hints take many forms. The simplest sends an entire range to one place. And we've actually implemented that in the reference implementation. We anticipated variants that might map a range to a list of alternatives ordered by what the DVM would like you to do. That might be multiple alternative addresses for the same host over different fabrics. So if you don't have an RDMA connection, then the second most preferred thing would be to use the TCP connection. Or in some hypothetical cases, the distributed volume manager that spans racks, for instance, might be aware of its host's placement and might give them different answers based on where they are, so they can read from the nearest replica. If you look at the simple hint table at the top, you'll see that we expect to be able to have a simple hint refer to I/O direction. So you could direct reads to one place and writes to another. So your hypothetical two-node system that did mirroring and had an allowed reading from its replica might balance reads across those or direct reads from the host to its nearest replica. They may still want to do writes all in one place to maintain, very strict ordering. So those are simple hints. They map an LBA range to one place or a set of places. An algorithmic hint, this class of hints performs a function on the LBA to determine which target it goes to. So striping is a simple example. Striping is actually not implemented yet in a reference implementation. We're not sure precisely what its parameters should be. So we'll get into that later. That's an area that prospective users can contribute to, what striping parameters they need. An algorithmic, the Ceph hashing hint is another example of an algorithmic hint, probably the most complicated one, where on each I/O we have to perform the rjenkins hash function on that LBA and then look up the target in a table. FYI, the hashing hint does not do the entire crush operation. In case you were wondering, we only have to do the hash function. if you'd like to know why, then take a look at the example scripts in the SPDK repository that will construct the hash hint, and you'll see how that works. So redirectors, it's assumed that redirectors are going to get hints from targets that overlap each other and may contradict each other because the state of the cluster may change. You, at different point in time, may learn something from another target that conflicts with something the first one sent. So the redirector, the host redirector, resolves that however is most beneficial to itself, and starts with you ignore the ones that refer to targets that you can't connect to until you can. They combine specifically to just like IP routing rules. If you have a hint that refers to a large extent range and another hint that refers to a subset of those LBAs, then for that subset, the shortest, basically shortest prefix matches. So the shortest rule applies, and outside that rule, then the enclosing larger rule would apply. That's the expected usage model here. So a distributed volume manager could, for instance, direct reads to the parent image and then send specific hints to direct reads from the child image to wherever those differences were stored, which might be in different places on different nodes. We expect, ideally, a redirector and a host can keep all the hints it's given, but maybe not. If for some reason there's a large number, it's really not to anybody's advantage to describe your volume with a huge number of location hints. That's in part why the algorithmic hints, actually that's really why the algorithmic hints exist, so that you can express complex things by a function in one hint rather than a million little hints. But if it's necessary for some pathological reason, hosts are free to drop the ones that they determine are not helpful to them. A host is advised to keep the ones it's using and only discard the ones it doesn't seem to be using. And the assumption is that it can, with the learning mechanism, when an egress redirector ends up forwarding I/O from that host, it can send that hint again, even if it's already sent that hint to that host, as long as it's not, you need to rate limit that. But in theory, they can relearn hints that they've had to have forgotten. So the idea here is that since all the targets are functionally equivalent, meaning they can all complete all the I/O, some of them are just way faster at it than others, then missing hints or stale hints or any lag in your host catching up with the state of the cluster impacts the performance, but not its correctness. So this is in contrast to other distributed storage systems where the hosts must be in perfect synchronization with the back end. That's one of the explicit goals of ADNN here, is that loose, best effort, eventual synchronization is good enough. So the distributed volume manager abstraction was introduced to contain a couple of concepts and lump some functions together, and also to define the boundary of coupling. So the diagram at the right shows a hypothetical distributed volume manager that is composed of, as you can see, 4 storage nodes, and a box on the left that represents all the cluster logic that decided, I've got this yellow volume and I'm going to provision it in 4 extents across all 4 nodes for some reason. You as the distributed storage architect will make those decisions for whatever reasons you need to make them for. And in this case, there's 2 other volumes, the green one and the purple one, that are only on a couple of nodes for some other reason. In this diagram, we show a box called Discovery Service that these hosts at the top would use to discover the target endpoints in all these storage nodes. So all these hosts would come up, consult the Discovery Service, make connections to all those storage nodes. And those storage nodes, they're NVMe over Fabrics targets, so they will recognize the host and decide whether they're going to let it connect or not. And with the LUN masking features, decide which hosts see which namespaces. So let's say, for instance, the host on the left is supposed to see the yellow namespace. So when it connects to these storage nodes and it lists the namespaces, it'll see the yellow namespace on all of them. And then shortly thereafter, it'll start receiving location hints from those storage nodes because they are ADNN redirectors. And very shortly after that should have in this case, because it's pretty simple, should have a complete map of where all the extents are. So any distributed storage system that does block and can host a NVMe Fabrics target on its storage nodes can be a DVM. So the idea is that you can make your distributed storage system into an ADNN DVM. This, the boundary here, the coupling boundary, means that these hosts are not tightly coupled with the distributed volume manager. So inside the DVM, these redirectors are all explicitly configured by the cluster coordinator or whatever it is you have put in your distributed volume manager. They're all steered explicitly with exact placement location in this case. The host redirectors aren't. They connect, they do their best to pay attention to everything they're told. If they don't, the DVM egress redirectors make it work anyway. It's just not as fast if they don't pay attention. So it's probably important to point out, I guess we mentioned this in the previous slide, redirectors can forward I/O to each other over the fabric, but if your distributed block storage system has a private interface for getting I/O between your nodes, and there's a pretty good chance it does if it exists now and spans nodes and it can support NVMe Fabrics as in a kind of a gateway mode where all the I/O comes to one node. You've got to have some mechanism for forwarding I/O between them. So you can use that, or you can use NVMe Fabrics. It's a choice of the architect. So we have constructed a reference implementation of the ADNN redirector. This is an SPDK BDEV. This is your basic building block for constructing prototype ADNN systems. These are configured with JSON RPC just like any other BDEV with one or more targets and optionally with some initial location hints. The idea is that we want one redirector implementation that we can use everywhere. But as you can see, the host redirectors and egress redirectors have slightly different behaviors. The data plane is really identical, and it turns out almost everything else is identical too, except how they start up and are configured. So in a host redirector, with the goal of stateless configuration to the maximum extent being one of the overriding principles there, we've enabled the redirector to inherit its namespace and GUID, its size, and its alignment from its default targets when it starts. So when it starts up and it's told, here's your targets you should talk to, it before it actually enables itself for being opened, it will interrogate those things and determine those properties for itself. Now, an egress redirector can't do that because it's the source of truth for this. So the distributed volume manager control logic basically configures these things, and it will tell them exactly, you have this NGUID, you have this size, you have this alignment, and it probably also configures each of them with authoritative hints that says this extent is here. Don't believe anybody else that tells you otherwise. So this SPDK BDEV responds to pass-through get log page commands in order to pass hints to the things connected to it. It's a little strange for a BDEV to do that, but it doesn't break anything. It's supported. You can handle pass-through commands. And of course, it uses the same mechanism to read hints from its targets. So redirector BDEVs can be connected in one SPDK process just using the BDEV interface. So you can construct toy networks this way without having to deal with all the fabric stuff. And in fact, all the system tests for the redirector do that and rely on that a lot. So this reference implementation also supports the scripts you need to generate the hash hint for an RBD image. We don't have a lot of time to go into the details of how that works here, but in the script subdirectory of the redirector BDEV, you'll see some support stuff that you run on your Ceph cluster, and it produces a JSON file with the properties of your Ceph OSD pool and that image that you want to export via ADNN, and that JSON file is basically fed into the redirector in its add hint command. So the interface to Ceph is really small. You'll run an ADNN redirector on each of your OSD nodes and one on your host, and there's no changes to Ceph required. All the things that ADNN needs to get from Ceph, it gets with the Ceph CLI tools. So the distributed volume manager we chose to test the ADNN reference implementation with was Ceph for a number of reasons. A simpler distributed volume manager might have been an easier choice, but of course there aren't any. All the candidates don't really, your DRBD based things and Gluster even don't benefit from ADNN currently because they put whole volumes on one node. You may have a federated bunch of DRBD hosts that replicate, but the typical infrastructure will choose one of those from the pool and put your volume there. It'll spread all the volumes around all the nodes, but all the volumes are all in one place. So in order to make those benefit from ADNN, we would have had to change them, and that was out of scope for this. So Ceph is well understood, and it already benefits from ADNN. So our test setup here, the details are listed in the top paragraph. We won't go over them, but the bottom line is it's a virtual cluster. And that was okay because the goals we have to prove here are that the hash hint, which only does half of crush, it only does the hash part of it, and we get the rest of it out of the Ceph CLI tools. We needed to demonstrate that worked. So we set up a test system that has one virtual network that Ceph uses, and another virtual network that we have only NVMe TCP traffic on. The goal is to show that by plotting the network utilization metric on Grafana, basically, that you can see that normal Ceph traffic takes the Ceph network and doesn't use the NVMe TCP network, and that the ADNN components only use the NVMe network. So we wanted to show that the traffic does the expected thing in three test cases. One is normal RBD, like I said, and the last one will be ADNN, where we have the host using ADNN talking to its egress redirectors in all of the OSD nodes. And in the middle case is your alternative to ADNN. If you want to use NVMe for Fabrics, but you have a a storage backend, then one solution is add a gateway. So you can either have a gateway in a separate host, which of course means you need a separate host, or you can put that gateway in one of your OSD nodes. That kind of adds a lot of load to one OSD node, but what they all have in common is that almost all of your I/O then traverses your fabric twice. So one of the goals here is to show that ADNN doesn't do that and can compare those things. We also wanted to confirm that the CPU utilization in the host was lower with the ADNN egress redirector, with the ADNN host redirector doing the hashing than it was with the native RBD client. And then, of course, the latency should obviously be lower with ADNN taking one hop over the fabric than it is if you have a gateway. So that was the final goal. So here are some of the results. We have these two graphs. The top trace here is the network bytes per second on our Ceph network, and the bottom one is the bytes per second on our NVMe TCP network. Inside these, each of these graphs has a trace for each OSD node and the single client we were using. So there's a lot of traces on here, and in all cases, receive traffic from each node goes down from 0, and transmit goes up. So the white box on the left highlights the baseline RBD case. So as you'd expect, there's traffic only on the Ceph network. We ran the FIO job there, and of course all the traffic only occurred there. In the middle graph, or the middle time interval, is the gateway case, where the FIO job was still running the host. The host used NVMe over Fabrics to connect to an NVMe TCP gateway in one of the OSD nodes. which then submitted it to RBD. And because there are 8 OSD nodes and 7/8 of the I/O is on not that node, you can see that we have almost as much Ceph network traffic in the second case as we did in the first case. And of course, we have all of that traffic on the NVMe TCP network. So you're paying for it almost twice as much. Okay, so then the last time interval here is the ADNN case, where the host with the same FIO job used, it had the consistent hash hint configured in it, and it was connected to all it was connected to the NVMe fabrics target in all of the OSD nodes, and of course those targets also had egress redirectors in them, which didn't have much to do, but except behave like redirectors and be recognized that way. It's worth noting that that was present on the left too, just to keep things simple. We didn't change the SPDK app in the OSD nodes at all through this test. It was always there. So in this case, we confirmed no traffic at all on the Ceph network. All of it is going from the host to the correct OSD node, and then doesn't have to be forwarded. And the reason this, so I mentioned on the previous slide, this OSD pool is unreplicated. So that means that even if it was replicated, you'd still see Ceph traffic even if you got the I/O to the right node, and it would be pretty difficult actually to separate the replication traffic from the host traffic on the Ceph network. So we just turned off replication in that pool, because obviously we can't, getting I/O to the right OSD node doesn't eliminate the replication traffic. If your distributed volume manager needs to do replication, you need to do that whether the I/O gets to the right place or not. So anyway, this is a victory declared here, because the no I/O was forwarded, and the host redirector did the right thing with the hash hint that we generated from the Ceph CLI tools. The latency goal here was more or less shown. I don't have a table for it, but the summary is that at Q depth 1, we found that basically all of the test cases behaved very similarly. There was really no difference between the RBD and the gateway case, and the ADNN case did increase write latency, not read latency, but it did increase write latency measurably, about 1%. We don't know why. A little bit surprising, but there you go. Now at QDEP 64, we had a surprising result, which was that, well, first of all, the gateway result was as expected. The latency was higher for both reads and writes with the gateway case. I didn't detail that out here. But ADNN read and write latency was significantly faster than even the RBD case. We're not 100% sure why. We have some theories, but we haven't confirmed it yet. It still needs to be investigated. It was repeatable. Since it's not completely understood, probably shouldn't count on that result. I mean, it makes a certain amount of sense because we spread the work over multiple OSD nodes. So that if that's why, then a more heavily loaded Ceph cluster might not see this benefit. So those are the latency results, and then that leaves the CPU utilization results. So what we wanted to show again was that with ADNN, you use less of your host CPU on storage. And if you are a cloud provider, the CPU cycles you spend in your hosts on your cloud storage are CPU cycles that you can't bill your clients for. So in that case, you may be happy to shift that work out of your host and into some other node, but we're guessing you would prefer probably not to dedicate an entire gateway to that. So in this graph at the bottom, we have measured and plotted overall CPU utilization in the Ceph client node when we ran the workload with RBD, and again when we ran the workload with ADNN. Now, the astute reader will maybe wonder, since this uses an SPDK application in the host, well, how can we measure the CPU utilization? We did that with some Grafana query magic that combined because these are 8-core VMs, it combined the OS CPU utilization statistic, or excuse me, the OS CPU utilization metric from cores that did not have SPDK processes running on them with we had to write an exporter for the SPDK thread stats on the virtual machine nodes that ran SPDK process. So, and this is all aggregated to show you a node CPU utilization for these 8 core nodes. And the 2 test cases that we're interested in here are the one on the left, where we ran the workload at 30K IOPS with kernel RBD, and this other one out here with the bottom red line ends, where we ran that same workload into ADNN on that same virtual host. And these red arrows pointing at the difference show you that out here when we switched to ADNN, it was different by that much. And the fine print up here, where I say that we save half a core at 30K IOPS, I'm calling that 6.5% of 8 cores in that between those red arrows. So, you know, approximate, but definite. You can see, and this is repeatable, and it's whether that's significant depends on who you are and what your I/O rates are and whether you care about host CPU utilization. It's worth noting that this, since all the I/O has to go to librbd if you're going to Ceph, so we have to make the librbd call somewhere, and we're not doing it on the host, so we're doing it now on the OSD nodes. In this case, there were 8 OSD nodes, so I measured. It's not shown here, but I measured that the incremental CPU utilization increased on all of the OSD nodes by about 7% of 1 core, which is they're all 8 core machines, so it was a small increase, but it translates to 7% of one of their virtual cores. So obviously there's no free lunch. If you're a cloud provider, you'd be perfectly happy to push that work out to the Ceph OSD nodes. You may have multiple backends, for instance, and this keeps all the overhead out of the host. And it also, obviously, as we covered before, the hosts don't actually know this is Ceph. They get a hash hint, and if they understand it, they use it. If they were connected to a different DVM, they'd get different hints, but the hosts don't change. Regarding how the client CPU utilization scales, we again, this is a virtual cluster, so 40K was as high as we can go with some of these workloads, and it was actually lower with some of the others. So this graph on the right represents all of the points we were able to measure, and the color scheme, the green lines are the ADNN test cases, and the not green lines are the kernel RBD ones. So there's 2 lines in each case. One is queued up 16 and one is queued up 64. The Y scale is number of cores, so it's translated back to the number of cores in that host, and the X scale is thousands of IOPS. So you can see that as the IOPS increase, the number of cores increases for all these things. I don't know if it looks this way to you. Kind of looks to me like the green lines don't slope as high as the blue lines, but admittedly we've only got 3 data points here. In any case, the green lines obviously are lower in all the cases. So this graph at the left only shows RBD and ADNN compared at one specific performance point, but this graph indicates that it was lower for all of the performance points. So we can't quite claim that it trends lower, that it'll scale higher. We ran out of gas in this test cluster, so we need to do this again with a physical Ceph cluster to see whether that really scales. So the notion of getting I/O to the right place in one fabric hop can extend to smaller scales than the whole fabric. So it, depending on your distributed storage system architecture, if you have multi-socket storage nodes with storage devices and network controllers in both NUMA node, your DVM might benefit from setting up an egress redirector in each NUMA node, and then constructing your set of hints to the hosts to direct I/O from the fabric directly to the right NUMA node. Now this diagram indicates you're doing this with Ceph. Now that's possible. The support scripts that I constructed don't enable you to associate an OSD with a with a NUMA node. They lump all the OSDs in the same host together into one target. They could be extended to identify the NUMA node for each OSD. There's actually enough information out there that the scripts have to do that. I just didn't do that because I was testing this in a virtual cluster. This might be more interesting in a DVM that has less logic between the fabric and the media. So if you're constructing a DVM that's closer to a bare SPDK app where there's not a lot of code between the fabric and your SSDs, but you've got a dual socket system with SSDs in multiple sockets, then the set of hints you give your hosts, you might benefit from sending them directly to the right NUMA node and avoiding all that UPI traffic. That depends on your architecture. So this is our call to action. We would like you to use ADNN with your distributed storage system. We have published the reference implementation as a patch to SPDK. You can see the URL here points to a patch set in the SPDK Garrett repo. This is based on the last SPDK release as of time of this presentation. So if you follow the instructions similar to the ones under that bullet, you should be able to clone that branch and build a working version of ADNN yourself. You can, we hope there's enough documentation there for you to set this up on Ceph yourself. If you have Ceph as a backend, even a small Ceph cluster, a couple of nodes, the support scripts and everything are there for you to set that up and feed some I/O into it. What we'd really like you to do is consider or attempt to connect ADNN to your distributed block storage system, whatever that is. So it's an open question whether we've initially defined the right set of location hints to address the common needs. We've used our collective experience with distributed storage systems at this company and others to construct those, but we don't know until you try it. So, and finally, the ADNN code lives out there as a branch and a candidate for merge, but it has no users, and it's really too early to even consider that because we need to iterate with the people who would actually use it before we know what form it should take. So now is the time. If this is useful to you, to come and participate and comment and tell us where we got everything wrong and or got it right if that happened. And so please do that. We also need to work out what would need to change for this to be standardized. So as we said before, this works, in air quotes, meaning it may violate notions of distributed namespaces and what's allowed and what's not, but you can do it. But those issues all need to be resolved somehow before this could be standardized so that we could make ADNN components that interoperate with each other, which of course would be the goal. So that's the kind of feedback we need from you. And please look at the patch. You can comment on it there, or you can just email me. And thank you.